Download this code from codegive.com, link in the description below. Understanding assertion failure, byte offset, contents, and size during parsing, a deep dive. Assertion failures during parsing are a critical tool for debugging and ensuring the correctness of your parsers. They provide valuable information about where the parsing process went wrong and the state of the input at that point. This tutorial will explore the meaning of assertion failures, their connection to byte offsets, the relevant content that triggered the failure, and the size of the data being analyzed. We'll use Python and the struct module to illustrate these concepts with concrete examples. 1. What is an assertion failure in parsing? A parser takes raw input, often a file or byte stream, and converts it into a structured representation that your program can understand and manipulate. This process often involves making assumptions about the format and content of the input. An assertion is a statement that checks if these assumptions hold true at specific points during parsing. If an assertion fails, evaluates to false, it indicates that the input does not conform to the expected format, and the parsing process has encountered an unexpected condition. Assertion failures are crucial because they prevent your program from proceeding with potentially corrupted or misinterpreted data. Instead of silently producing incorrect results or crashing unexpectedly later, an assertion failure signals a problem early in the process. 2. Byte offset, pinpointing the error location. The byte offset is arguably the most important piece of information provided by an assertion failure. It tells you the exact position in the input stream, file, byte array, etc., where the assertion failed. This position is measured in bytes from the beginning of the input. Knowing the byte offset allows you to examine the problematic data directly in a hex editor or using Python slicing features. It's your guide to finding the source of the issue. 3. Content, the trigger for failure. The content refers to the actual bytes of data that were being examined when the assertion failed. It's the specific sequence of bytes that caused the parser to recognize a deviation from the expected format. Examining this content is crucial for understanding why the assertion failed. Was it an unexpected value? An incorrect data type? A missing field? The content reveals the nature of the problem. 4. Size, the extent of the problematic data. The size refers to the number of bytes that were being examined or considered as a unit when the assertion failed. For example, if you're parsing an integer that's expected to be 4 bytes long, the size will be 4. The size helps you interpret the content correctly, particularly when dealing with multi-byte data types or structures. 5. Example, parsing a simple file format with assertions, Python and struct. Let's illustrate these concepts with a practical example. Imagine we have a simple file format that consists of a header and some data records. The header contains asterisk a magic number, 4 bytes, little endian integer, 0x12345678. Asterisk a version number, 2 bytes, little endian integer, 1. Asterisk the number of records, 2 bytes, little endian integer. Each data record contains asterisk an ID, 4 bytes, little endian integer. Asterisk a value, 4 bytes, little endian floating point number. Here's the Python code to parse this format, using assertions to validate the input at each step. Explanation asterisk. 1 parse underscore file, file name, function asterisk. This function encapsulates the parsing logic. 2 file opening and reading asterisk. The file is opened in binary read mode, RB, to read the raw bytes. The data equals f.read, line reads the entire contents of the file into a byte string. 3 offset variable asterisk. This variable is crucial. It keeps track of the current byte offset within the data byte string. It's initialized to 0 at the beginning of the file. For header parsing *, the code then parses the header fields, magic number, version, number of records, using struct.unpack. Struct.unpack, data offset plus 4, 0, this line does the following. Data offset plus 4, slices the data byte string to extract the 4 bytes starting at the current offset. This represents the magic number. Struct.unpack, unpacks the extracted bytes as a little endian, unsigned integer, I. The first argument to unpack is the format string. *0, struct.unpack returns a tuple, even if it only unpacks a single value. We extract the first, and only, element of the tuple. 5 assertions *, this is where the magic happens. After unpacking each field, an assert statement checks if the value matches the expected value. Assert magic underscore number equals 0x12345678, F assertion failed, magic number mismatch at offset. Expected 0x12345678, got 0x magic underscore number x. If magic underscore number is not equal to 0x12345678, the assertion fails. The string after the comma is the error message that will be displayed if the assertion fails. Crucially, this error message includes the offset value, so we know exactly where the error occurred in the file. It also includes both the expected and actual values for debugging. 6 Data record parsing *, a loop parses the data records in a similar manner, extracting the ID and value for each record. 7 Error handling *, the try, except block catches the assertion error exception. This is critical because it prevents the program from crashing when an assertion fails. Instead, it prints a helpful error message including the details from the assertion and returns none to indicate a parsing failure. It also catches file not found error. 8 Create _valid _file, and create _invalid _file, *. These functions create example files for testing. Create _valid _file, creates a file that conforms to the expected format. Create _invalid _file, creates a file where the magic number is intentionally incorrect, triggering an assertion failure. Running the example *. When you run the code, you'll see the following output. * for the valid file. * for the invalid file. Notice how the assertion failure message for the invalid file tells you that there was a magic number mismatch. That the error occurred at offset 0. That the expected value was 0x12345678. That the actual value found in the file was 0x99999999. This information is invaluable for debugging. 6. Using a hex editor to inspect the data ***. With the byte offset in hand, you can now use a hex editor, like hxd, or a similar tool, to directly inspect the bytes in the invalid_data.bin file at offset 0. You will see that the first 4 bytes correspond to 99999999 in hexadecimal, which represents the incorrect magic number 0x99999999. 7. Understanding the struct format strings ***. The struct module is essential for working with binary data in Python. The format string tells struct.unpack how to interpret the bytes. Here's a breakdown of the format strings used in the example. Little endian byte order, important for cross-platform compatibility. If your data is in big endian format, use *I, unsigned integer, 4 bytes. *h, unsigned short, 2 bytes. *f, floating point number, 4 bytes. *c, character, 1 byte. *s, character string, number of bytes needs to be specified before the s. 8. Advanced techniques ****. Custom error messages ** craft error messages that provide as much context as possible. Include not just the offset and the expected / actual values, but also the name of the field being parsed, the version of the format being used, and any other relevant information. Conditional assertions *Use conditional assertions to check for specific conditions that are only valid in certain scenarios. For example, you might have an assertion that checks the value of a field only if a particular flag is set. Fuzzing combine assertions with fuzzing techniques. Fuzzing involves generating a large number of random or semi-random inputs and feeding them to your parser. Assertions will then catch any unexpected behavior caused by malformed or invalid input data. Logging consider using Python's logging module in conjunction with assertions. Log detailed information about the parsing process, including the values of variables, the byte offsets, and the results of assertions. This can be helpful for diagnosing problems that are not immediately obvious. 9. Handling endianness ***. Endianness, byte order, is a crucial factor in binary data. Little-endian means the least significant byte comes first, while big-endian means the most significant byte comes first. The struct module allows you to specify the endianness using the little-endian and big-endian prefixes in the format string. Always make sure to use the correct endianness for the data you are parsing, otherwise, you will get incorrect values. 10. Dealing with variable length data ***. Some file formats include variable length data, such as strings whose length is specified in a preceding field. In these cases, you'll need to read the length first and then use that length to read the string. Assertions can be used to validate that the length is within reasonable bounds and that the remaining data is sufficient to hold the string. 11. Conclusion. Assertion failures are your allies in building robust and reliable parsers. By carefully crafting assertions, you can catch errors early, pinpoint their location with byte offsets, examine the problematic content, and understand the size of the data involved. Combined with tools like hex editors and the struct module in Python, you can effectively debug your parsing logic and ensure the integrity of your data. Remember to always handle assertion errors gracefully and provide informative error messages to assist in debugging. Practice using assertions in your parsing code, and you'll become much more proficient at creating parsers that are both accurate and resilient.